Hey everyone, this is the last lecture before we have officially mastered the standard normal distribution. We're going to go over a challenge problem, so let's get started. Alright, I'm going to pull up my computer and we're going to go through an example together. See you there. Alright, so let me discuss how this is going to work. I'm actually going to set up the problem first, and then I want you guys to pause the video. And then we're going to come back and discuss the solution to this problem. So here I have the standard normal distribution where the middle is 0, I have an average of 0, and a standard deviation of 1. Now, the idea is we're going to be solving for a z-score, actually two of them. So here's one of the z-scores, it's right here. We need to figure out what this z-score is. I'm going to give you some information in a second here, but there's also another z-score that we need to solve for, and it's this one on the other side, which is actually negative z. And the idea is the distance between from 0 to z and from 0 to negative z are the same. The idea is these are just the same z-scores. One's the positive z-score, one's the negative z-score. So just keep in mind that if you found one of them, you've also technically found the other one. They're just opposites of each other in terms of negative and positive. Now, what I will give you is the area between these two z-scores. So I'm going to draw the region, the area under the curve, between these two z-scores. And I'm going to tell you what this area is. This area is exactly 0.95. So like 95% of the bell curve. So it's a pretty big chunk, and it's not really well drawn out because, I mean, it looks like we got some leftover stuff over here that looks much greater than 5% of the bell curve. But regardless, just let's imagine this is drawn to scale and that this blue chunk, this blue region, occupies 95% of the region below this bell curve. So the question is, how do we find these z-scores? And this is going to require a little bit of geometry, so what I want you guys to do is I want you to pause the video and try this on your own. So pause the video now, try it on your own. Alright, so if this was a really tough problem, that's totally normal because this is one of the more challenging problems that a statistics professor could ask. But the idea is, we know that these two z values are more or less the same. They're just opposites of each other. That's really important. Because what that does tell us is, well, if we find one, then we find the other. So that's really important. So I just need to find one of these. Now, I'm going to draw two regions here, and I'm actually going to use the same color for both, and there's a reason for that. I'm going to draw this region right here. I'm just going to shade that in, and I'm going to draw this region right here. Now, I want you to, if you haven't figured out this problem yet, that's perfectly fine. I want you to pause the video and I want you to think about this question. What is special about these two areas? What relationship do they have between each other? So pause the video and try to give that an answer. So this is kind of hard to see, but I'll explain why this is. These two red regions are exactly the same area. And the reason for that is because this blue region is symmetrically aligned in the bell curve. And so the area to the left is the same as the area to the right. So this region right here is the same as this region right here. The red regions are exactly the same, meaning they're the same area. Now, if this blue region takes up 95% of the total area, how much percent is left? 5%, 0.005. So we have 0.05 is the leftover area. Now that 0.05 is divvied up between this region and that region. And since they're the same regions, then that must mean that this region has an area of 0.025 and this region has an area of 0.025. That way they're the same areas, and if you add them together, you get the leftover 5% there. So these two regions both add up to 5%, and they're equal in size. Now, that was a little tricky, But this is where the problem gets a little bit easier, because now if we take a look at this z-score right here, we have the area to the left of that z-score. It's 0.025. So how do we find the z-score given the area to the left? Well, we have to go to our chart. We're looking for what z-score has an area to the left of 0.025. So we're going to head over to our z-table real quick. And I'm looking for a z-score. Let me real quick allow editing on this. We're trying to find a z-score. So these are the z-scores over here with an area of 0.025. So can you find 0.025 somewhere in here? Pause the video and try to find it. Let me see if I can find it. Keep in mind, it is not this. This is not 0.025. That's actually 0.0025. But we're close. I think 0.025 is right here, 0.0250. So what z-score is that? I know it's a little hard to see, but it's negative 1.9. This is the zeros, the ones, twos, 3, 4, 5, 6. So this corresponds to z equals negative 1.96. So now let's go back over to our table. I'm going to pull that up real quick. Not our table, our bell curve. I apologize. So let's go back to our bell curve. We know what the z-score is. It's negative 1.96. And so that means this z-score, we know because it's symmetric, this z-score would have to be the positive 1.96 because they're both equidistant from the number 0. That was part of the setup of this problem. And therefore, we have found these two z-scores. Now, this problem is actually relatively important, especially when we get into confidence intervals later on, understanding what the z-star is for an 85% confidence interval, 90%. If this is a little confusing, which it should be, that's perfectly understandable because we haven't gotten to that part of this course yet. But that being said, this is actually really important. Now, I do want to mention something that's also really interesting here. Do you guys remember the empirical law or the 68, 95, 99.7 rule? If you don't remember that, we've done a lecture on that, a couple lectures on that actually in this course already, so check those out. But look at that second number there. What is that second number? That second number is 95. What does that 95 represent? I'm going to remind you guys that 95 represents, that's what it says, according to this rule, that 95% of the data is between 2 standard deviations away from the mean. Now, what's the standard deviation of this bell curve? Standard deviation of the standard normal distribution is 1. So let me use a different color here. So if I go 2 standard deviations away, so that's 1 standard deviation, 2 standard deviations, in both directions, then the region between those two numbers is going to be 95%. But that's actually not completely true. Unfortunately, the 68, 95, 99.7 rule, this is going to be kind of interesting, is a lie. It's completely a lie because it's actually rounded. So remember, the first number corresponds to 1 standard deviation away, second number represents 2 standard deviations away, and the third one, the 99.7, represents 3 standard deviations away. But it's actually not. It's actually rounded. It's not 2 standard deviations away. It's actually 1.96 standard deviations away, which 1.96, if you round to the nearest tenths place, is 2. So it's 2 and negative 2. But keep in mind, it's technically not exactly 2. It's 1.96. And that's actually really important. I know you might be thinking like, well, why don't we just, fix this and just round that to 2 and round this one to, hold on, you guys probably can't see that. Round that to 2 and round that to negative 2. There we go, problem solved. Actually, we can't do that, and there's a reason to that. Later on, when we talk about experiments and what makes an experiment good, you're going to find that that little bit of a difference matters because if your test falls in between 1.96 and 2, which we'll talk about what that means later on, then people start getting into some serious debates on whether or not their experiment actually works, because technically you're outside of the region, which would verify your results. But according to this rule, it doesn't. So which one do you follow? You follow the Z table. And so that's why I'm trying to tell you now, the 68, 95, 99.7 rule is technically not correct. It's close, but it's not 100% correct. We have to rely on this mathematics in this Z table and understand that it's actually 1.96 standard deviations away, capture 95% of the data. And it's actually a little bit different for 68% and 99.7% as well. This is actually not exactly 1 standard deviation away, and that's not actually exactly 3 standard deviations away. So understand that there is a little bit of a discrepancy, but just keep in mind when you actually apply this stuff later on, most of the time you can use these numbers for 1, 2, and 3 standard deviations. So anyways, thank you guys so much. I'll see you in the next lecture.